Alrighty, let's see where we left off. We left off, I think right there, right? We had just talked about like local area and wide area networks.
Correct.
Not familiar? Okay, cool. Well, then just to recap that piece, we talked about computer networking, we talked about domains, compilers. Okay, so local networks and wide area networks. So local networks are like anything that's connected to a router through the internal interface. Like a router has two IPs on either side. If you're on the local side, then it's usually 192.168.1 as the router's IP, and all the IPs underneath it like know that they can connect to other things on that local network. And then there's the wide area network side on the other side, which has an external IP assigned by your ISP. We'll talk about IP addresses a lot during this particular lesson, but the focus is, or the thing to know is that IP addresses are always kind of assigned downward. So your internet service provider assigns the ISP to your router, which assigns, and that router then assigns IP addresses to the local devices. We might talk about that more, but in general, if you have a phone, your phone connects through wireless signal to your router or to your wireless access point, which then connects over Ethernet to your router, which then connects over Ethernet to a cable modem or a fiber optic line, which then connects to a bunch of routers that go out to the internet. And we talked briefly that there's this thing called a DNS, domain name service server, which is if I go to a website and I type in the human readable text, that human readable text kind of reaches out to the DNS server through this route. And that DNS server says, hey, tell me what the actual IP address is for this domain. And then it resolves it. And then it goes out to the internet, grabs the actual internet information, sends it back. Okay. Any questions there before we start moving into other things that are good to know?
No questions.
By the way, I can't see your faces.
You said IP is based downwards. It starts from the basically the modem.
When they're first assigned, when you first connect to a network, you get assigned an IP address, and that IP address is assigned from basically the router down. So like my phone has an IP address that's assigned to the router it's connected to right now. The router gave it that IP address. That router got assigned an IP address by my internet service provider. And so on and so forth.
So if you configured a static IP address, in theory, you could get the router to tell the cable modem
basically
that this is what I want to be.
Yes. You assign a static IP. So there's dynamic, I was going to mention this, DHCP, dynamic, I can't remember what the name of it is. And then there's static IP addresses. DHCP automatically assigns a free IP address to a device and it kind of remembers that device unless you click forget network, which is what most people use. You can assign static IPs, like in flight tests, a lot of times you do because you want to know what the exact IP
what we're going to do
in the router based on the MAC address of the device. And the device, each device, hardware device, has what's called a MAC address. And it's like a bunch of nonsense characters that are just specific to that device. Like every device is unique in the world of the MAC address. You can force a device to have a specific IP, and then the router knows to check the MAC address, make sure that it matches, and then say that that device has this IP, which might be 192.168.2. For instance.
Okay.
We'll
and if you have two
that
things
here.
Okay, I'll stop. It's gonna be too much.
It'd be good to get into the IP addresses before we talk to your questions. So another thing to note is how is this information flowing, right? There's are you guys familiar with the electromagnetic spectrum?
Yeah, somewhat. You know the term.
So basically the electromagnetic spectrum is how photons travel through the universe. which can get very deep into Einstein's theories and quantum mechanics very quickly, but we'll keep it very high level. You have like the visible spectrum of light, you have like radar, you have like IR, UV, gamma rays, like you have this whole spectrum. And basically it is wavelengths of light that have different like frequencies and different wavelengths. And if you have a shorter wavelength, you have a higher frequency of cycles. So you could have like cell phone signals happen on a certain band of that spectrum versus like radar happens on a certain band, IR happens on a certain band, visible light happens on a certain band. And I will just quickly bring up the electromagnetic spectrum so that you guys can see it here. Electromagnetic spectrum. And I will share my screen once I get there. Here's a good classic. So used to working on Mac now that I'm like, where's my screen share?
Lucky you.
Share the screen. Share Chrome. Electromagnetic spectrum. So this is a good one over here. Actually, this is the standard one. And I want to try to like make this full screen and see if we can go there. Okay, so the electromagnetic spectrum goes from extremely low or high frequency short wavelengths down to extremely low frequency low wavelengths. And the visible spectrum that your eye can see in terms of photons is here through the cones and rods in your eye. IR sensors are here. UV sensors UV light like the sun produces is here. X-rays happen here. And I think this is gamma rays happen here. Long radio waves that can get very low happen down here. AM, FM radio happen here. Microwaves happen here, and you can see the actual frequency and the wavelengths and numbers here. It's important to know that this is a giant continuous spectrum. The thing that is actually floating around in that spectrum are called photons, which are like massless pieces of energy. It moves at what's called the speed of light. Before we get there real quick though, I want to show you this diagram. This is useful diagram to look at. You've got gamma rays that are used in like medicine to like target cancer or kill cancer cells. So certain like high frequency wavelengths can actually get dangerous. They can damage DNA and all kinds of different stuff. X-rays, a little bit less dangerous, but long-term exposure is not good, which is why your doctor hides behind a thing if they take an X-ray of you. Used to view like objects inside of bodies. They can see through like different types of items. Ultraviolet, obviously not good for the skin. It's what the sun produces. Visible light, you can see that there. The blue wavelength, that's maybe important, is actually harder to project on TVs because it's it's the fastest wavelength of the visible spectrum. And blue or red is the easiest to project on TVs because it's the slowest wavelength. If you want to get into actually why, I don't really know. I've seen that before. I've seen the math before, but something about higher frequencies are harder to visualize. Infrared, it transmits heat. So you can have like an infrared camera that can see these wavelengths. So it's actually seeing the heat that's being transmitted. Just to be clear, all of these transmit energy. It's just that you'll feel a lot of heat here. If you do really high, like intense things here, I think that this also translates, can translate a lot of heat really quickly. Don't quote me on that though. I'm not an EOIR guy. Microwaves do stuff here, as well as like cell phone signals in the microwave spectrum. There's also like if you ever get a ham radio license, which is actually really fun to get, you'll get to see which like frequencies you're allowed to use in the spectrum, and then broadcast and AM radio down here. Now there is an inverse relationship to wavelength and frequency, kind of a 1-for-1, and you can tell the math. Like frequency is like 1 over wavelength, I think, and per time period. So you can kind of tell like how fast things are. Now let's, any questions here? I'm going to talk about speed of light here in a second, but any questions here?
All good here.
Cool. All righty. Let's jump back to sharing. This little nugget. So the speed of light, so photons, right? Photons are little pieces of energy that fly throughout the universe. It is actually, if you want to get really deep into Einstein's theories, it is the speed limit of the universe. It is the velocity of the universe. And it's actually, in reality, a constant ratio to other pieces of the universe. If you want to get really deep into what light is. And we could talk about that in depth, like the fact that if you were a photon, time doesn't mean anything to you. You're both in your current spot and in the final destination at the same time. But if you're human relative to that speed of light, then time actually does mean something to you. Anyways, so the reason I brought that up is if you have a fiber optic cable, for instance, or you're a wireless signal, you're traveling at the speed of light. If you're a wireless signal and you're traveling through air, it's diffracted and slowed down a little bit, so it's slightly less than the speed of light. If you're in a vacuum, it's actually the speed of light, which is 3,000 times 10 to the 8th meters per second. You might remember that from like an undergraduate school or something. And then the other thing to note is that if you have a cable modem, you're actually sending electrons, not photons, through the routing system. So if you're over Ethernet, I think Ethernet is photons, maybe it's electrons. No, actually, I think it is electrons. But fiber optic is speed of light. So electrons have a speed. It's slightly less than that. I could look it up right now. Speed of electricity. Speed of electricity is 299,000 or million meters per second. So it's a lot less than light, but it's still like crazy fast. So anyways, that's just good to know. We can transfer information by both electron particles and by photons. IPv4 interfaces. Now we're going to jump down to talk about the actual like structuring of IP packets. I know that was a lot of context information, but I like to give it. So there's IPv4 and IPv6, and I'll talk about why there's IPv6, but IPv4 is a thing that you'll use in most of your flight testing and your home routers. Though some modern routers use IPv6. Internet Protocol version 4 is what that stands for, and it looks like this. It is a series of octets, 4 octets. So the maximum number of IP addresses, just by the math that you can have on a base 10 math system, which we're using here, 0 to 9, the X being replaced with 0 to 9, is 999 million, 999 or 999 billion, 999 million, 999,999. And so why did I bring that statement up? It's because we've run out. Believe it or not, we have more than that number of devices connected to the internet for that purpose. So many years ago, I think in the early 2000s, we actually had to come up with a new system that had way more IP addresses to connect way more devices. And it's got like a quintillion worth of like ability, because it's got like a lot more octets and stuff. So what do we do? Because we had run out, we never thought we would back when we invented this, I think in like the 60s or 70s, but like now that we've run out, we've developed so many devices, what we've done is internet service providers have like a consortium, and they lease the IP addresses that they give different devices that are on the wide area network. And then what we've done is we've crafted internal local area networks that are different than the wide area networks so that we could get around this limitation. And so your IP, your internet service provider has provided your home with an IP address that's one of this, 999 billion. But your internal network has its own set of IP addresses that the external world doesn't know about. It just knows to reach you at your ISP assigned address. And so we get around that where you can have a lot more local devices at home, but we reserve the ones that are in the wide area network so that we don't run out of IP addresses. And then there's certain chunks that are reserved for different things. And you can go down deep rabbit holes as to what these are all kind of reserved for. Here's actually, maybe I got that wrong. And for some reason I wrote this down, and this is the number that you could have in existence. 209. Yeah, I don't remember exactly the math behind this, but there's a limit. So let's talk about, so any questions on IP address structure, right? Any of these numbers take on 0 to 9.
No, but that's insane that we've run out.
Yeah. So subnet mask is basically a way to restrict routers to only assign a certain set of IP addresses. It's basically like, this is not an IP address. This is a subnet mask that looks just like an IP address in format. But they really fall into a few classes: Class A, Class B, and Class C. And the idea is that I can have multiple devices within a local area network that can't talk to each other, but can talk to each other on basically these subnets. So if I put 255 in this octate, that means it's locked. If I put 0, that means it's not locked. So if I go into a router and I say that you have a virtual local area network that is like 192.168.0 or .10, and I put 255.255.255, then the only thing that can be assigned, the only number of addresses you can assign is in that last octet that could talk to any other device on that local area network. Now, I know that's confusing, so I have an example here. It still sometimes confuses me. But if the base network is 192.168.0.1, that's like your router's IP address, or a virtual network IP address, which is basically a virtual router. And I have a subnet mask on top of that. That's 255.255.255.0. Then a legal address is 192.168.94. Oh, sorry. This arrow is broken. It's actually supposed to be 255.255.0.0. Class B, if it's a Class B network. 192.168.194.83 is legal to assign to a device on that network. 192.142 is illegal to assign because that second octet is locked by the 255 here, subnet mask, to 168. So I couldn't assign a device on that network this IP address. So you can start to subdivide networks through subnet masks. So I can have two virtual networks, but they could be in the second octet locked to two different things. So all the devices that I can assign to those networks are locked to that. So if I go to a particular device and I see that, oh, it's a 168 device, but I have these different subnet masks, then I know that it's assigned to that virtual environment or that router environment. Does that make sense? I know that's confusing, can be confusing.
Yeah.
Yeah, your router basically,
yes.
You can assign it a subnet mask, or you can basically say no subnet mask, like 0000. Everyone can talk to everyone.
Mm-hmm.
This gets deep into networking, and what I would recommend actually is just to know the concept that subnet masks exist, and that you can subdivide your network further with subnet masks. And then if you ever come across a point where you need it, Google some more, watch some more YouTube videos on how to actually implement it. But your router basically will ask you to configure these when you first start, or have a default. Mm-hmm. But sometimes you don't want everyone on a local network to be able to talk to everyone, and that's kind of the objective. You can get really deep with configurations of these things. IP packets. We got 7 minutes left. We'll talk about IP packets now. Just getting really deep into the weeds. So I will caveat that this subnet mask, this format, and this IP address is for IPv4 only. They get more complicated when you move to IPv6 addresses. In fact, did I write anything about IPv6? No, I didn't here. It's worth a Wikipedia read. So this is the way that an IP packet is actually structured in terms of bits and octets. So IP packets, when they're constructed, are actually like binary packets when they're sent across the wire. And let me refresh my brain here. So those 3 numbers that can be assigned 0 to 9 actually correlate to a binary, basically, or sorry, not those 3 numbers. The octet itself, like an IP, what am I saying? An IP packet has a certain number of bits that you can send in an octet. So the address is the address, but the actual contents of the IP address packet are structured similarly to the way that the IP address like octets are. It has 4 octets in it, meaning that it can send 32 bits of information. I believe I said that right. 0 to 31, 32 bits of information. And this is different than like 192.168, but I think the reason they did the same thing is they want to have 4 octets per IP address while they have 4 octets for the actual address itself. But the bits of information are, a bit can either be 0 or 1. And let's just talk about these first few bits of information. The first octet of information of bits correlates with, now I'm starting to get myself confused, but it correlates with the version and header information, and something called time to live, basically the amount of time that the router needs to worry about having it. And then some additional protocol information about the IP, like TCP, TCP, UDP type stuff. The total length, the fragment offset, the header checksum to verify the whole packet got there. We could talk about that later. The source address, the destination address, and then options for the actual information stored. And I think I said that wrong originally. An IP packet looks like it can have up to 448 bits because it's 32 bytes and there's 8 bits per byte. And I bet 8 times 32 is 448. I had to guess. I'll be honest, I'm not a master of like IP packet inspection, and like I can do it with Wireshark, but I'm not an expert here. Let me do the math there to make sure I said that right. Calculator. Sorry guys, I'm like relearning this as I tell you about it. 32 times 8, 256. Why did I say 448 bits there? Let me see what my notes here say. I might have to come back next week and give you guys a little bit more deep dive on IP packets when I actually look more in depth at what they are again. But the bottom line is that an IP packet has binary format data that's going to be transferred. It has the source address of where it's coming from, the sender, and then it has the receiver destination address of where you're trying to send it to. So when the mailman, which is the router, gets it, he knows who the sender and the receiver is. And let's see. Oh, I do have a little bit of IPv6 information here. And there's a lot of complicated information about it, but it's all within the context of a router system being able to know how long to keep the packet, where to send it, how to verify all the data made it to the other end and that the packet didn't get like corrupted along the way, which is how you do that with something called a checksum piece of software that can basically back out any amount of text into a specific long form number that's very unique to that text, so they can guarantee that all the information get there, you run a checksum. If the checksum matches the checksum in the message, then you know that you've reached all the information's gotten there. Okay, I want to set this aside just for a second, but are there any questions on IP packets before I talk about these two things, bandwidth and ping?
All good.
I'm sure there.
Yeah, there's lots of questions, but not.
I'm
Yeah,
not as prepared this week as I
recap of
thought I
that
was when I came into it to describe IP packets. Let me do some research for next week and try to get you guys some information about the actual internal structure. It's been a few years since I've dealt with the internal structure of an IP packet as I'm like looking at it. Great Wikipedia article on it though. And you don't have to deal with this as much. At a software level, I'll talk about how you actually just send it. Usually you just need the IP and you send it, and there's functions to serialize it for you. I want to close by talking about bandwidth and ping, because these are two useful topics. So when sending information over a network, there's something called bandwidth, which is the amount of information you can send per time. Usually it's measured in megabits per second. So if you have and just for note, bit is 1 0 or 1 number. Byte is 8 0 or 1 numbers. So if you have megabytes, that's different than megabits. Megabytes is 8 times the amount of megabits. But
Wait, can you
megabits.
repeat that? Bits is 0, 1, 0, 1 numbers.
Yes.
Okay.
Yes, it's a 0
That's
or
big.
a 1. It's a bit. It's like a light switch, whereas bytes is more than that.
Okay.
And it just determines how much information you could transfer across the network. Ping is how fast the information gets to the other computer. We'll talk about both of those next time because they're both important. It's like, how much water do I have going through, and then how much pressure do I push to make it go as fast as possible? That's kind of how it works, or maybe a crude analogy. We'll come back. I will talk about the numerical schemas of like bits, gigabytes, and bytes, and I will try to come more prepared, talk about IP packets next week.
Okay.
I got to